Hi everyone, I'm Reid, a PhD candidate at the School of Cybernetics at Australian National University, and I'm recording today from the unceded lands of the Wadawurrung people here in Geelong on the southwest coast of Victoria.
And I'm Liz Williams, a senior lecturer, also in the ANU School of Cybernetics. I'm joining you here today from the unceded lands of the Ngunnawal and Ngambri people in Canberra, the capital of Australia. And today we're going to cover the socially responsible representation of accents in voice data.
You're probably familiar with voice and language technologies such as automatic speech recognition. They're increasingly deployed in systems such as voice assistants, chatbots, and mobile applications in contexts as diverse as healthcare, industrial automation, customer service, and even inside your car. These technologies are driven by machine learning, which is a statistical approach to identifying patterns in large volumes of data. The voice and speech data that are used as inputs for machine learning models are typically stored in specially formatted files. These files often encode features of the speaker, such as their gender, their age, and accent. And here's an example of such a file from Mozilla's Common Voice project. We can see that the file contains data that describes the gender, the age range, and the accent of the speaker. Accent is a broadly defined concept within linguistics, but in general is taken to be how a person's spoken language differs from the local spoken language. Accents differ by characteristics such as phonetics, intonation, and lexicon. For example, a person in the north of England might say trap and bath using the same sound, but a person from the south of England might say trap and bath with a different a sound. Intonation is where emphasis is placed during speech. In Australia, for example, we often rise up at the end of a sentence. Lexicon refers to the words and phrases used within an accent. In Geordie accents in the north of England, you might say nout to mean nothing or ben to mean child. Combined, these variations often encode sociolinguistic identity information about a speaker, such as their geographic origin, ethnicity, socioeconomic status, and group membership. And accent data may be included in voice datasets used for machine learning. This is so the trained model better reflects the characteristics of the real-world setting into which it's deployed. For example, a model intended for use in southern France may be trained on a dataset that has a lot of samples from contributors who speak with a southern French accent. Just like many other machine learning datasets, bias, the systematic and unfair discrimination against individuals or groups, may be present in voice and speech data across several axes of variation, such as gender, age, and accent. These biases may then be propagated to machine learning models when they're trained upon this data. Language technologies that use the machine learning models may therefore exhibit accent bias, where the speech data from individual contributors or groups of contributors who speak with a specific accent is acted upon differently to that of other individuals or groups. Accent bias can manifest in a variety of modes. For example, work by a team from Stanford University led by Alison Koeneke found that speech recognition services from leading cloud providers all perform less accurately for speakers of African American English. This means that voice assistants and other cyber-physical systems that use speech recognition are less likely to work well for these speakers. Rachel Tapman in 2017 showed that YouTube captions performed less well for certain speakers. And here in Australia, the name Ken Behrens became synonymous with inhabitants of Canberra after it was mistranscribed during a press conference instead of the demonym Canberrans. We're also seeing accent bias manifest in the desire by recent startups to change people's accent in real time, ostensibly to make it easier for the listener to understand a speaker with an accent. The effects of speaking with an accent are also present in the justice system, where juries can be swayed as to the guilt of the accused based on their spoken accent. Accent bias in language technologies, while based in statistics, has tangible consequences in the real world. So, what leads to accent bias? And importantly, how might we be able to address it? We'll start with voice dataset creation. During this process, the categories a speaker belongs to, their gender, their age, their accent, are decided upon and assigned by the dataset creator using a process called annotation. When a dataset creator annotates a dataset, they have to decide on the categories that are used for annotation. Accents can be categorized in different ways. Some standards for representing a spoken language, like ISO 639, don't allow for the representation of an accent within a language. They just let you represent the language itself. Other standards, like BCP 47, allow a country code to be combined with a language to better represent variation. For example, BCP 47 can differentiate the Spanish spoken in Mexico from the Spanish spoken in Spain. But even then, this may not be granular enough to distinguish between the variation within countries. In British English, a Geordie sounds nout like a Scouse. And in Spain, a Castellano speaker from Barcelona sounds nothing like their Andalusian compadre. We don't yet have standards for representing this more granular distinction. Challenges throughout the data and machine learning lifecycle can also contribute to accent bias. Firstly, the accent of the speaker may not be recorded at the time that the voice data is captured. Even if the accent is recorded, it might use a label which is too broad, like British English, and so the variation in accents is not well described. This means the machine learning practitioner doesn't know what accents are in a dataset, so it makes it hard to intentionally balance the dataset that is used for training the model. Moreover, if the machine learning practitioner doesn't have any way to measure the bias of the trained model, such as by evaluating against a bias corpus, then it makes it harder to continually improve the model because there's no way to direct or target improvement efforts. In most machine learning models, there is a trade-off between granularity and generalization, and this is also called precision and recall, or sensitivity and specificity. This is illustrated well when we think about wake word spotter models that are used to wake up a voice assistant. And don't worry, I'm not going to say anything that will wake up your voice assistant. If the model is too sensitive, then the voice assistant wakes up when you didn't speak to it. But if the model is not sensitive enough, then it doesn't wake up when you do speak to it. Granularity and generalization also apply to other models used in speech recognition. So there are two key machine learning algorithms in modern speech recognition systems, and we're going to take a look at those. The first is an acoustic model. The role of the acoustic model is to take speech data in the form of audio files and transcriptions and predict a character, usually a character in an alphabet or an ideograph from a language like Chinese or Japanese. The accuracy of an acoustic model is measured by character error rate, a percentage score for how many characters the model predicted correctly. Acoustic models tend to be more accurate if they are trained only on speech samples from a particular accent using granular data. That is, data that is annotated with granular accent categories. The second type of model used in speech recognition is a language model. A language model covers a domain or a set of vocabulary. The vocabulary reflects the phrases that are expected to be encountered where the speech recognition model is deployed. For example, if you're using speech recognition for medical transcription, you would expect the language model to cover medical terminology. If a word is not in the language model, it is considered to be out of vocabulary. While there are methods available to guess out of vocabulary words, they're just less likely to be predicted. The purpose of the language model is to map characters to words. And if we recall that one-dimensionality of accents is lexical difference, the use of words or sentences that distinguish the accent from that which is usually or predominantly spoken, then it becomes clear how a language model can contribute to bias. This is because words used in the accent may be out of vocabulary in the model. The language model needs to be more general to include a broader vocabulary, so less granularity. The tension between granularity and generalization seen in speech recognition is grounded in the annotation and labeling of accents in voice and speech data. If data is labeled with high granularity, machine learning practitioners can make informed decisions about the contents of training sets. Conversely, however, granular labeling of data allows us to create models that classify what type of accent is being spoken. Cast our minds back for a moment to our two Castellano speakers, from Catalunya and from Andalusia. Let's now imagine that the Spanish government uses voice technology to deliver services. And let's consider the political tension in Catalunya recently with the secessionist movement. Might the algorithm treat people who speak with a Catalan accent differently? By labeling accent data in ways that allow models to be inclusive of accents, we also create a situation where speakers of those accents can be discriminated against. A double-edged sword. So how should this trade-off be handled in a socially responsible manner?
While there are several actors involved in the social responsibility of accents in voice data, we're focusing here on practitioners and policymakers because of their ability to influence outcomes and catalyze change. Here, we provide several provocations for each of these groups. For ML practitioners working with voice and speech data, the overwhelming provocation is one of provenance. Where does my data come from? Metadata management is well established in other fields, such as librarianship. And while there are some nascent efforts to apply this to machine learning datasets, such as datasheets and data statements, we don't have standards for voice data. Not yet, anyway. So our first provocation here is, what might metadata standards look like for establishing the provenance of voice and speech data? And if those standards were available, machine learning practitioners would still need to be able to integrate them with their existing toolchains and platforms. So, what might ML toolchains look like that facilitate working with metadata standards for voice and speech data? Both of these provocations presuppose a commitment by the individual practitioner to understanding the provenance of data and making intentional data selection choices to reduce accent bias. Even with standards and toolchains available, the practitioner must appreciate the importance and consequence of bias and allow this to influence their work. This requires adoption of reflective practice. That is, being aware of how we think, feel, and act, and the assumptions we might be making. What might reflective practice look like for machine learning practitioners working with voice and speech data? We'll now turn our attention to policymakers, who are primarily concerned with designing and enforcing accountability measures that reduce harms and accentuate benefits. One key consideration here is defining accent categories that are appropriate to the policy context. These might differ between service delivery, healthcare, or education. Different features of the accent might be needed to ensure equity. So, how might policymakers decide upon relevant and culturally appropriate accent categories for their locales and contexts? This becomes particularly important as we consider how datasets can be shared between companies or made available openly. A dataset that is fit for purpose in one context may not be in another. So, what data sharing constraints are appropriate for voice and speech data? Next, policymakers need instruments to ensure accountability. There's been little work done to date on providing benchmarks or points of reference against which regulators and auditors might assess accent bias in datasets or in trained models. What might bias corpora or other references for equitable recognition of accents in language technology look like? And how might they be designed with input from the affected communities? All these provocations are interrelated and won't gain momentum without the strong desire to have technology that works better for more people. We warmly invite attendees from this workshop to work with us to explore these provocations further. Thank you so much for listening to our presentation. We'd be delighted to engage with you further. Our contact details are listed here.